Okay, hi and welcome to the lecture number 11 on convex analysis. So I don't know if anybody is listening right now. I don't know. So anyway, we had still some unanswered questions from last week. Maybe I'll just say a few words just for you to know what's it about. So we talked about the Moreau envelope a week ago, and there was this simple question: if you have a positive, so a non-negative function f, what about its Moreau envelope for any positive parameter? Is it still non-negative or not? And the answer is obviously yes. If you check the definition, you see that so Moreau envelope is defined by minimizers, and of what you take f and add a little bit of a square centered at some point, and then take the minimum. But since you add a square, the values of the function which you minimize are only larger than the values of the original function, so you only minimize non-negative functions, and so the answers are always the minima are also always non-negative. So this obviously holds. So what about strong convexity? If you have a convex function and take its Moreau envelope, does this improve on the convexity of the function? And well, the answer is no. And the simplest example is the constant zero function is obviously convex, but its Moreau envelope is still constant zero, so it's not strongly convex. It does not improve on that. But it improves on differentiability. So the Moreau envelope is always differentiable, which is really a big thing. Okay, so here the answer is no. Okay, there was that. And so now I have here I have a question on subgradients. So we're going to talk about the subgradient sum rule today a little bit. The topic is applications of subgradient, but actually it's more examples and applications. But anyway, so the question here is: does the subgradient sum rule hold, and under what conditions does it hold here? So the setup for the question is: you have a proper convex and LSC function f, and another function g which is convex and differentiable. And then the question is, what do you know about the subdifferential of the sum? So first of all, the sum need not to be differentiable, since f not need to be differentiable. So that's one thing. And then the answer option is: does the subgradient sum rule holds at points where f is also continuous? It holds for all. It even holds subgradient plus gradient. And so this notation here means, so this is a set that's a singleton set, so that means that all elements here get so you add this element to all elements of this. Or the answer may be it depends on further information, and actually there's more than one correct answer. Okay, maybe just think about it for some time, and then answer it, and then at some point I will want to answer it maybe later. Okay, so for the topic of today, it's lecture number 11, and it's about applications of subgradients. So what can you do with subgradients? And actually it's not only application, it's also end examples. So that's what it's about today. So first, so once you've seen the subgradient sum rule and conditions which ensures that it should hold, of course it would be interesting to know if there's counterexamples. So examples where the subgradient sum rule does not hold, and it's not a real counterexample because this only can be if the conditions are not fulfilled. So, but anyway, so here example 11.1 has multiple things, and so the question. So here's the first example where one example where the sum rule does break down. And if we check what does we need for the subgradient sum rule to hold, we need that there's one point where both functions are finite and one function is continuous. So both functions finite, one function continuous at some point. So that's okay. It was a little bit too. Yeah, we need one point where both functions are finite, and another point where the function is continuous. Okay, so here's the counterexample. So we have we can take f as the indicator function of the non-negative numbers. So if I do the plot here, that would be, so f would be the function which is 0 here and jumps up to plus infinity at 0. And as g, we could also take some indicator function, but let's make it a little bit. No, we can't. Let's make it a little bit nicer. So we take minus the square root of minus x for x negative and or non-positive, and infinity for x positive. So how does that look? So this here is f. Okay, so for x smaller equals 0, then this is positive, so this is the usual square root, and this is the positive square root, but we take the negative one. So this is the function which looks like this, and also jumps up to infinity like here. So let's calculate everything. So what about the subgradients, or what's the subgradient of f? So that is more or less simple. Of course, the subgradient is empty for negative x, because then the value is plus infinity. Of course, the subgradient is just 0 for positive x, because at these points the function is differentiable, it's constant. And so what happens at x equals 0, that's the only interesting point. So then it's just by inspection, by visual inspection, it's the set of all slopes of slopes of lines which you can fit under the graph, and so all negative slopes work, and even slope 0 works. So here it's the interval from minus infinity to 0, 0 included. What is the subgradient of g? And again, simple is it's 0 for x positive, the empty set for x positive. But also, okay, let's do it like this. So for negative x, that's also simple, because for negative x, the function g is differentiable, which means the subgradient is a singleton and only contains the derivative, which is in this of this function, it's 1 over 2 square root of minus x. So, and the final point is what happens in x equals 0. Here at this point, so this does not work there. The square root is not differentiable in 0. So, but what slopes can we fit under the graph? Actually, none. No slope at all. So, because the only thing which would work, so every finite slope would intersect the square root function over here and would not be totally below. So, actually, it's at 0, the subgradient is already empty. Okay, so that means what is the sum of the subgradients? Yeah, well, for negative x, it's empty because of this. The empty set plus something is still the empty set. You take all elements of this and add that, so there's none, so there's none. And for positive or non-negative x, it's again empty, because you take all elements of this and add that, it's again nothing. So it's always empty for all x. That's bad. Or maybe not. So what about the subgradient of the sum? So the sum, what is that sum actually? Yeah, what is it? Let's do it like this. So of course, for negative x, it's plus infinity, because f is plus infinity. Plus infinity minus something finite is still infinity. So this is for negative x. For positive x, it's the same thing, because this function is already infinite. So this holds for all x which are non-zero. But at 0, both functions are 0. So the sum of this function is it's actually very simple. It's the indicator function of the singleton 0. So only here it has a value, and it jumps up to plus infinity right there and also right there. So and then it's also very simple to see what is the subgradient of that here. It's all slopes which fit under the graph. So the graph is actually just this single point. So and the subgradient of the sum is actually very, very large, because all slopes fit under the graph. So it's actually the real line. Of course, at x equals 0 and empty otherwise. So we see n0, the subgradient of the sum is much larger than the sum of the subgradients. So it's really a proper inclusion, and it's even as extreme as it can get. The sum of the subgradient is empty, and the subgradient of the sum is everything which could be possible. Let's check so that's how it is. And let's check what's going on in the proof and why doesn't the proof work. So it can work because we'll see that it's the conclusion is wrong. Remember that in the proof of the subgradient rule we had used these two sets. One of the set was x alpha, y alpha, such that alpha is larger or equal to f of y, and the set C2 was the sets of y and alpha such that minus g of y was larger or equal to alpha. That's how it was actually. So let's check how this and then the argument was we're going to separate these two sets because they are disjoint. And so how do these sets look in this case? Let's do it up here. So first, the set C1 is basically it's just the epigraph of f. So you take all this positive authent here, and this is C1. And what is C2? C2 is kind of the subgraph of G flipped. If you have a look, it looks like this. This is C2. So, and the sets touch here in the origin, okay, but still they are two convex sets which only share boundary points. And only actually they only share one boundary point, that one here. So we can separate them by a hyperplane. That's what the separation theorem gives us. But what hyperplanes can we choose? Of course, no hyperplane with a positive slope. That does not work at all. And also non-hyperplane with a negative slope, because all negative slopes would intersect here. The only hyperplane which really fits in between is the one which is vertical. So because this infinite slope here at 0 kind of squeezes out all the other hyperplanes which we could try, which are not vertical. Okay, so and we saw in the proof, so that this is a vertical hyperplane, which means we really cannot turn it into a subgradient. Subgradients have correspond to finite slopes. Okay. That's the reason. So, and you remember the proof worked like this. We constructed this separating hyperplane and then had to deduce that this hyperplane is not vertical, which we obviously can't do here. Okay, that was that. And for the chain rule with the linear maps, it's even simpler. We take again a function f, which is a little bit like the function g up here. It's infinite for negative x, and it's minus square root of x for positive x. So it really looks like this. Same thing basically, but now on the right hand side, on the left hand side, and we only consider the point 0 right now here, and then it's again like before, the subgradient of f at 0 is the empty set. But now let's take the kind of degenerate operator 0, which is the 1 times 1 0 matrix, and then the function which you considered phi of x was f of ax, which is just f of 0 for all x, which is 0. So f of ax is constant 0. And then we have it, so which means that the subgradient of phi at 0 is actually 0, while a times the subgradient of f of a0 is actually empty, and so this is actually larger and not equal. So it's simple as that. This can also fail. Okay. Good. So so now what about the question in chat? Maybe we can wait. So maybe you just give me a sign if you answered the question, then you can. Oops. So now for some positive results. So it's just called a corollary because it's nothing much to do to prove it. So the corollary now really goes into directions of applications. In this lecture and the next, and I hope also the next week, we're going to do some more application-oriented stuff, which means we're going to derive some algorithms to solve optimization problems. So the corollary goes like this. If we have a convex, proper convex LSC function, so proper convex and lower semi-continuous, and we take a set, a subset which is non-empty, closed, and convex, so both kind of the regularity which we always need, such that the domain of F really intersects the interior of C. So there's a point where F is finite and we are still also in the interior of C. What we then have, we can say that X hat is a solution of the constraint minimization problem. You want to minimize F, but only over X and C. So of course you know already that we really don't need this constraint down here. We could put the constraint actually into F if we would like to, so setting F to plus infinity outside of C. But let's keep it like this. Sometimes it's beneficial to treat these things separately once again. So for example, if F is actually differentiable or continuous everywhere, for example, then this would be a nice function with finite values all over the place. And if it's differentiable, you could just use the gradient, for example. So the thing is, we can now characterize this with two conditions. The first condition, this X hat, of course, has to be in C. And the second condition is that 0 is an element of the subgradient of F of X hat plus the normal cone of X hat again. Okay, and this is, so why does this hold? Of course, so the function which we need to consider would be F plus indicator function of C. That's the function which we would like to consider. And we know that so X hat is actually in the argmin of this unconstrained. So, and then by Fermat's principle, we know that this is the case element if and only if 0 is in the subgradient of F plus indicator function of X hat. That's Fermat. And now, can we apply the subgradient sum rule or not? Yeah, and well, we can, because so this is actually it's equal F of X plus subgradient of F of X, subgradient indicator F of X or X hat, and the subgradient, this is the subgradient sum rule, and why is it fulfilled? Yeah, it's because of that. There is a point where both are finite and one of them is continuous, and this is that one. So the indicator function is continuous at the points which lie in these intersections, because they're in the interior of C, and if you're in the interior of C, there's a whole neighborhood where the indicator function is constant 0, so it's of course differentiable. And at least it's differentiable, but it's also continuous. So this condition here allows, or not allows, guarantees that the sum rule here works. And then the final thing we should notice that the indicator, the subdifferential of the indicator function of some C is actually equal to the normal cone. Okay, so on this characterization here is kind of the principle of Lagrange multiplicators in some sense. Why? Just graphically. So let's consider we have our set C would look like this, and our function f. It's hard to depict. Maybe I could draw level lines. So let's say the C looks like this. These are the f looks like this. These are the level lines of the f. Actually, that was bad. So that's okay. Okay, I could do it like this, but now the picture is bad because now the minimum would be like here. This would be x hat, and the formula still applies because that's the minimum. It's inside C. Okay, that's nice. And the characterization says it's inside C, and the normal cone in interior points is actually only 0. And so that's it. Okay, the big picture was bad. The picture I wanted to draw was like this is C, and the level lines go like this. So the unconstrained minimum would be outside. So these are the level sets of F. So and how do we find now a point in C, which is minimal for F? Yeah, well, this is exactly where the level line kind of touches touches the C tangentially. So at this point here, where the this is actually where the minimum should be then, and why does it correspond to this condition here? Well, the subgradient of this point looks like, so the level sets are all smooth, the subgradient is only the gradient, and it points in this direction, and with some length, I don't know, the length depends on how dense the level lines are here. So, but the normal cone here is actually also this line here. Okay. Yeah, that's it. Actually, that's the negative subgradient which I saw. The subgradient actually points into the other direction, because it's this is where it goes up, this is where it goes down. Otherwise, the function would not be convex. So this is the subgradient here, and this is the normal cone. And of course, you see we can choose some element in the normal cone such that these two things add together to 0. And this is basically the same picture you paint for Lagrange multipliers. Okay. So this is actually the rule of Lagrange multipliers in some sense. Okay, there are so that's nice, but there are a few reformulations which you can use, because we kind of know how to describe being in the normal cone. So reformulations of star would be x hat is in C, and either the condition A, which means there exists a subgradient of F at point x hat, such that for all x in C you have subgradient in a product with x minus x hat is non-negative, or actually either or is not so, of course they are equivalent, so both of them can be fulfilled at the same time. There exists a subgradient of F at the point x hat such that for all positive gamma it holds that x hat equals to the projection of onto C of x hat minus gamma times P. So these are both so being in the set C and this, or being in the set C and that, both of them is equivalent to the optimality, and both of them characterizes optimality for the constraint minimization problem. So why is that? We have the condition, so of course x and C is the same, and this condition here is fulfilled if and only if. So what does that mean actually? So these are two sets in general. So in this picture this was a set, and this is just a single vector, but it can be two sets in general. So one way to characterize this here means that there is a vector P in the subgradient of F, and minus P is an element of the normal cone. Actually, it should be heads all over the place here. A head and a head. So this is actually, so these two things are equivalent to that. This is how an inclusion with the sum of set values operators is decoded here. There has to be one element in here, and the negative has to be in there. And only if this holds, the sum here contains 0. Okay, and then if you write out what this means here, it gives you this assertion. So being this is a characterization of the normal cone, gives you exactly that. So actually this condition would be there exists a P such that this, and if you write down what this holds, it means that for all x and C it's like this. So writing out this gives A. Okay, that's one thing. And the other thing is, so this is for condition A. For condition B, we use the projection theorem, which is theorem 2.9, to say that this here is equivalent to say for all C it holds that kind of this x hat minus gamma P minus that, times x minus for all x in C times x minus x hat. This is non-positive, and now these things cancel out. That's a negative here, turning this into this inequality. So this is just by the projection theorem. These two things are actually equivalent. Also graphically, it makes a lot of sense. At least both conditions make a lot of sense. I would like to show you this because I find it a little bit surprising that it's kind of like for all positive gamma. How can that be that it's for all? But it's actually very simple. If you look at this here, so this point here is the optimal one. This here is x hat. And so it's also characterized by this. And what does that mean? It means this x hat should have the property that if we move from x hat any amount of any subgradient in the negative direction of a subgradient, so we move from here into the direction of the negative subgradient, which is now the negative subgradient is this. You can move any amount in this direction. But if we then project back to C, we end up exactly where we have been. So for example, this point is not optimal by this, because at this point, let's say the level set goes like this here, which means the subgradient would point in this direction, and if we go some amount in this direction here and project maybe from here back to C, we will end up there, and this is not the same point here. So if you're here, moving in the direction of a negative subgradient of f, brings you to this line, and no matter where you are on that line, projecting back to the set C always gives you something else than the point where you've started with. Interestingly, it looks like if you take the right amount of negative subgradient, then projecting back gives you something better than before. So of course, if you make very, very large step here and then project back, you may end up somewhere which is even worse than the point, but it seems like at least for a small displacement here, it may push you into the right direction of the minimum here, of the solution actually. Okay, so it turns out that this thing here can be turned into an algorithm. We're going to talk about that in the second half of the lecture. Okay, now comes applications. So first we're going to do it just by motivating and without proving anything, and later on we're going to prove something. Okay, say let's do a non-negative, a least squares problem. So a least squares would be, you want to minimize this over x. So and then what is given over x and r, what do you want to have? rd. Oh, and then I didn't think about, so the a. So what is given then is a is something like let's say n times d matrix, and b is an, or let's say m times d, and b is an rm vector. This is given, and then this is an ordinary least squares problem. You know that from a lot of other lectures probably as well. So it's of course you use this for linear regression. You may use this in numerical analysis, or you solve in numerical analysis whenever you have some imperfectly given data, and you want to and your model is that b has been generated by a times some unknown but desired x. Then you want to minimize these squares in case the b contains measurement error or something. So, but okay, and then you can solve this, for example, by solving the normal equations or by doing conjugate gradients or whatever. There are tons of possibilities here. Things get more complicated as soon as you introduce constraints. So let's do not minimize this over all x and rd, but maybe only over x which have non-negative entries. Does this? So what can we do then? Okay, so then the minimization problem would be like we minimize, and let's do it like this because it makes computation simpler, plus the indicator function of the non-negative auth. And so I think we draw it like this. So this is a non-negative least squares problem. So it's considerably more difficult. Okay, but There's also help from numerical analysis here, but kind of using convex analysis a bit. You write down the optimality conditions and see what you can do with this. Here's a very low-cost approach to that. So if you don't have time to read a numerical analysis book and figure out how you what would be the best method to do it, if you only have half an hour, but you want to have an approximate solution to some non-negative least squares problem, this is what you can do. So this is our set C here, to use the characterization we've just seen, we would need the projection onto the non-negative orthant. So, but that's simple. So projecting onto the non-negative orthant, so onto all vectors which have only non-negative entries, what do you do? So here is the picture. That is the set you want to project on. You are given some point, maybe here. How do you project onto that set? You just move over there. This is a projection onto C of X. So this is the set C. And if you're here, you just move there. If you're here, you just move there. So what do you do? For this vector, the second coordinate is negative, so the first is already positive, the second is negative, and what you do, you just set the negative coordinate to 0. And here the first coordinate is negative, the second is positive, you set the negative coordinate to 0. Both coordinates are negative, you set both to 0. So what you get is you do apply the max operator component-wise. And actually this is also written as X plus non-negative part of X. So that's the projection. Okay, first question, can we apply the subgradient sum rule here? Yes, we can. Why? This function is finite everywhere, at all points. Which means that it's also locally Lipschitz continuous at every point. Actually, it's Lipschitz no, it's not Lipschitz continuous, but it's even differentiable at all points. Which means any point here, and this set here has interior points. That's also important, right? We would need a point, an interior point here where the function here is this. So this should be finite, and this should be continuous there. So any point here works. That's nice. So subgradient sum rule is applied, and actually this answers the questions here. If we have proper convex and lower semi-continuous plus convex and differentiable, subgradient sum rule is always fulfilled, and because G is differentiable, actually this is also fulfilled. Okay. Good. So, and what in this case here, this let's take this here as f. Then the subgradient of f, because f is differentiable, is actually the singleton which contains the gradient of f, and this the gradient of f is A transpose A x minus b, which you can just say by linearization or however you like. So that means the characterization for optima gives us this is x hat has to be the same as if we do x hat move into the direction of the negative subgradient and project back to the non-negative orthant for any gamma non-negative. And this is now a fixed point equation actually. It's a fixed point equation for x hat. So why not just iterate it and hope for the best? So iteration, so fixed point equation, it's usually not a bad idea to turn them into iterations. Looks like this, starting with, let's say, any x0. Okay, and so you can just implement it, and we'll see. If you choose gamma not too large, then this is going to converge actually. Showing that it converges is not totally trivial because the iteration here is not a contraction. So Banach's fixed point theorem does not apply. If you choose gamma too large, it's simple to see that it's even is Lipschitz continuous with a constant larger than 1. If gamma is small enough, the Lipschitz is Lipschitz continuous with constant exactly 1, which you can see if this thing here lies into in the kernel of X somehow, then this is more or less the shifted identity, so Lipschitz constant would be 1. So Banach's fixed point theorem does not give you convergence, which also shows that this convergence may not be should not be linear convergence. Okay, we'll come to that later on in the lecture. So it does not follow from Banach's fixed point theorem, but it does follow, but it's some more work. Okay, we come to that later on. So what is the fact, which we're going to prove later actually, converges to solution if gamma is non-negative, actually positive, and smaller than 2 over the norm of A transpose A, the operating norm of that. If you do this, this is going to converge. And you can just try. You can just type it in, just generate some random matrix and a vector, choose some gamma like that, iterate, and you will see you will get a solution of the non-negative least squares problem. Okay. Yeah, maybe it's time for the break. What we're going to do is, for the rest of the lecture, we take this example a step further, write it down for both things here, for this non-smooth, analyzing this algorithm here in the non-smooth case, where this f is actually non-smooth, and then prove that it actually converges. What we're going to show there is worse than what we could show in this situation, because in this situation the f is actually differentiable, which makes life much easier when doing optimization. So okay, but it's time for a break. I'll be back in 2 minutes. Oops, there was it. I took the wrong screenshot. Sorry. Okay, anyways. So, a little bit more general than that. So we had projected, I don't know, this is also a name, I forgot what this is. So we can solve non-negative least squares with this idea. Gonna prove that, I think in the next lecture, maybe. Yeah, next lecture should give the proof. So let's get a little bit more general, but also do an analysis for that. So it only goes on the name example, but actually we're going to prove that the algorithm which we derive is actually converging. And the method is projected subgradient, and there's actually a typo in the lecture notes. It's subgradient method. I've written projected subgradient descent. You know the term descent for optimization, for optimization a lot, because, well, descent algorithm is an algorithm which always reduces the function value. If you want to minimize, that's the right thing to do, maybe. But actually this method is not a descent method. I think there's an exercise this week where you should prove that directions of the subgradient are actually not always descent directions. So even though at points there just maybe at points where the subgradient exists, not every may even be not every subgradient points into a direction of a descent where the function goes down. Sounds a little bit counterintuitive, but that's what it looks like in 1D. It always gives you the direction where the function goes down, but it's actually not true. Okay, a little bit more general than this here. We don't consider f from Rd to R proper convex and lower semi-continuous. C subset of RDO, and we allow the value plus infinity here. Non-empty closed and convex, and want to consider the minimization problem, minimize f over x and c. And actually now about min and not argmin, of course the problem can be considered the same, but actually it's slightly different. If one writes this, one is mostly interested in finding the minimum value. Of course, this is kind of what the notation emphasizes. And for the argmin, you would try to find at least some or maybe all x which assume the minimum value. That's a slightly different problem. Yeah. So only finding the minimal value, or also finding the x which realizes the minimum value. Okay, again, we already know condition B. X hat is the solution if and only if the projection onto C of x hat minus gamma p equals x hat for some p in the subgradient of f at x hat. And any gamma non-negative. Okay, so if we turn this into an algorithm, so it's not totally a fixed point iteration because we have this choice p here, but we can turn this into an algorithm by like this. We choose some p in the subgradient, so of course assume that this is possible, that we can do this computationally, and then set xk plus 1 equals that here, p, of course we should call it pk, projection onto C of xk minus gamma pko. So I try to use upper indices for vector valued quantities. So that could be like this. So, and of course we could also use a gamma k here. It's also not, we could also choose gamma k non-negative. Actually we should be taken positive because 0 doesn't make any sense, and you just stay where we are. So okay, this is projected subgradient method. So we do a subgradient step. So from x given xk, we move into the direction of one negative subgradient, and then we project back onto the set in case we've left the set, and then just see and iterate that. Okay, let's analyze this method a bit. So let's analyze. Let's say x star is a solution. And I have to write it's a solution because there's no way to guarantee uniqueness under our given assumptions which we now have. So we assume that. And then what we can consider is, let's write down what is this distance here. 2 norm squared of xk plus 1 minus x star. So the distance of the next iterate to our solution. So what we know from x hat as a solution, we know that the projection of x star is again x star because since x star as a solution has to be in C. So projecting back doesn't change anything. So just plug in what we know. So we know from definition that this xk plus 1, the next iterate, is the old iterate minus some step into the direction of a subgradient. And here this is actually that. Okay. So then there's one thing which we did not prove yet, but we're going to prove very soon. Projections are Lipschitz continuous. So remember that these are nonlinear projections. They project onto a convex set. It's not a linear operation. If you project onto a subspace, that's a linear operation, but projecting onto a general convex set is not a linear operation. But anyways, projections are Lipschitz continuous with constant 1. We'll prove that later. We could have proven it already, actually it's very simple, but we didn't do it up to now. Oh, so there are still a lot of lower indices left. Okay, there's one more, probably I check them all. Let's see. Xk minus gamma k pk minus x star, since projections are non-expansive, or this is what we want to call operators with Lipschitz constant, at most 1. Okay, and now just do we just expand the square here, giving us xk minus x star. So we expand the square with these two and that guy. 2 norm squared minus 2 gamma k, and then the inner product of pk with xk minus x star plus gamma k squared norm of pk. Oh, pk again, upper index. 2 norm squared. Oh, and now comes one thing. What we know now is that this guy here, that's the subgradient at xk. So let's write down the subgradient inequality at xk. We have for any x, it holds f of x is larger or equal to f of xk plus pk x minus xk. That's the subgradient inequality at xk. And we want to use it over here. So what we have to do is to evaluate it, or to use the subgradient inequality at the optimal point here. So you know that the optimal point is larger than that. So let's just an optimal point of the constraint minimization problem. But just let's consider it unconstrained. So this is where x star is in the unconstrained case, and this is where xk could be. And you see that this linearization here gives you a smaller value of that. So if we rearrange this to kind of separate this guy here, we could kind of put in the minus over here, then this switches already, and then make it larger by moving this over there. We get that xk minus x star 2 norm squared minus 2 gamma, and here we would have f of xk minus f of x star plus gamma k, what's gamma k, squared pk. So this is the subgradient inequality which we used here to turn that inner product into a different of function values. Okay, good. So what you see here, so one thing is nice. We see, so this is the distance to some optimal point at the next stage. This is where you have been before, and you see this is subtracted, but this is added again. Okay, but one thing is, so the xk comes from the previous iteration. It's also an element of C because it has been projected onto C. So this is the point which is called feasible for the optimization problem. It is in C, it's in the constraint set. And this is also in C, but this is the optimum, this is the solution, that's not the solution, which means that this value is larger than that, which means that this is always positive or non-negative. Which means as long as you're not optimal, this is strictly larger than 0, you really subtract something. Okay, but you add something. So you subtract something and you add something. So, but what is now the case is that if you make gamma smaller, this goes to 0 faster than that. Which means it seems like there should be a small gamma k such that this whole thing here is negative, because this is kind of more negative than this will be positive, at least in the limit. Which means that for a small enough step, you move closer to every solution. So we just assume that this is some solution, any, doesn't make the difference. So this already indicates that this distance to any optimum will get smaller if you choose a small enough step size. So that's just an observation. Observation, xk plus 1 minus x star may be smaller, should be smaller if gamma k is small enough. So of course you cannot estimate, really calculate when this is the case, because for this you would need to know the size of this thing here. So this is, you know, you've chosen your subgradient. So you can calculate its norm. Okay, that's nice. But you can't know that, and you can't know that either. So it's really, so it should be true for small enough, but it's not possible to turn it into something practical, because there's no way from this inequality to infer for what step size that this is the case. Because you don't know this and you don't know that, because you don't know the optimal value. Sometimes you know the optimal value and then it's possible. For example, for some problems you know that the optimal value is just has to be 0. That's possible. Then you can use this here. And actually, it's really like the case that if you have a good estimate of this quantity here, you could really turn this into an algorithm like that. Okay, but we can still guarantee something from this inequality. So one thing is we can't guarantee moving closer to the solution just from what we have here. Okay, that's bad. Okay, but let's rearrange. We rearrange this thing here into the following. We move this to the left-hand side. And that gamma k times f of xk minus f of x star is smaller equal to, and then we divide by 2 also, which gives us that gamma k squared over 2 times pk 2 norm squared plus 1 over 2 xk minus x star 2 norm squared minus 1 over 2 xk plus 1 minus x star 2 norm squared. Okay, so why is this good? Oh, it's not really good already, but okay, what is nice, and this is what kind of all the proofs we're going to do about convection relation algorithms use this in some way. You've got here the distance of two terms, one at the current iterate, one at the next iterate. You have the current iterate and you subtract the next one. So what we now do is we take these inequalities for k from 0 to some capital N and sum all these inequalities up. Summing inequalities is a valid thing. So what we get here is we sum from k from 0 to n, capital N, gamma k, f of xk minus f of x star, smaller equal to, this is again the sum from k to 0 to n, gamma k squared over 2 norm of the subgradient squared. And so what happens here? So we start with k equals 0, this is x0 minus x star minus x1 minus x star plus x1 minus x star minus x. It's a telescoping sum. So we end up with having the first one here, x0 minus x star 2 norm squared minus the last one. And the last one is xn plus 1 minus x star. Okay, that's nice. So it's a sum you could do also kind of to recursively from here if you like, but it's exactly the same thing. So this expression here is not too bad anymore, but it's still kind of complicated. You would like to show something showing that this goes to 0 or showing that this goes to 0. Actually, not both. Both is not possible as far as I know, because it's not true. No, it's not. You can't get the distance to any solution to 0. Maybe to some, but it's still unclear at this point. So, for example, what is nice is that if this right-hand side stays finite, and the gamma k, I don't know, if this stays finite, it means that this sum here converges. So if this would stay finite, this sum here would converge. And it would converge, so if you then would have that the gamma k do not to 0 go to 0 too quickly, then this has to go to 0 as well. Because otherwise the sum could not converge. That is not so easy to make this work without further assumptions, and so we assume further assumptions. So assume something which may help us. So one thing is we assume that the norms of the subgradients are bounded. So this is not always valid actually. It's, for example, it's not valid in the case of the least squares, nonlinear least squares problem. Because this assumption subgradients are bounded by L, this is actually, oh no, I wanted to have it like that. I think I wanted to have it like that, yeah, without there. It's equivalent to say that F is Lipschitz. F, yeah. With constant L. We didn't talk about this, but that's actually true. Okay, that's one assumption which is going to help us. And another assumption is not assumption, but now we do something else. We do another trick. So of course, this makes this sum very simple. This is just we can estimate further on the right hand side by estimating this by L square from above and take it out of the sum. Okay, but there's another trick because we also would like to separate the sum of this guy and that. So what we do now is we define the best function value which we got in the first n iterations. So this we define that as the minimum over k, or actually this should be starting from 0, but anyway. K equals 0 to n f of xk. So it's the best function value which you've seen on the first n iterates. And this is just an abbreviation which we want to make frequently. The best function value will be denoted by f star. And another abbreviation, so this is also a definition, another abbreviation is the distance at the 0th iterate. This should be, how do I do it? Oh, actually I don't use d0, I use d. And so d squared, I abbreviate this guy here. So to conclude what we have is, so we estimate this from above by L, we estimate this guy from above by d squared, and also we estimate this from above by just 0. So we just throw it away. It's a negative term here, which may be useful to showing that this guy is small, but actually we're going to hope that this is going to vanish for large n anyway, or at least get small, so we just throw it away. It's not going to help. The larger the n, the less it may help. So we just estimate it by 0. And here, what we're going to do here is we estimate this, this is larger or equal than f best. Okay. Now we put things together and get an estimate which can really which turns out to be really useful. So what we get with all these things is, on the left hand side now is again sum from k to 0 to n, gamma k, and then we have here the best function value among the first n iterations minus the best which is there at all, estimated from above by, here we got, oh this, sorry, we have this estimate by L squared, of course. That's now here L squared over 2 by, from 0 to n gamma k squared plus d squared. That's that. Okay. So now the good thing is, this is now independent of k. That's why we introduced this quantity here. So we can really view it like this. So this is independent of k, and we can pull it out of the sum. And now we have something nice. What did I do with it actually? Oops. Oh, so there's a lot of typos here. Oh boy. So. Anyway, this is all typos all over the place. Sheesh. All here. Okay, I have to redo some calculations here, but anyway, let's just move through and see if I can correct anything. So what we get here now? So what from this? We get an upper estimate for the distance, or of the best function value among the first n iterates, and the optimal one. So this can be estimated from above by just dividing this by that sum. There's a severe typo here in the handout and in the lecture notes. Okay, I'm going to correct that. K from 0 to n gamma k squared plus d squared divided by the sum of the step sizes. Okay, so yeah, and this now shows, so this shows if we choose the step sizes in a good way, then this right hand side may go to 0. Why? Because this sum of the squares may be much smaller than the sum of the step sizes themselves. So what we really need is here, we would really like to have that this would go to infinity and this should go to 0. Is that possible to get? That would be one thing, for example, for n goes to infinity. That's one way to think about it now. So if you choose the step size in a way, then this sum here gets arbitrarily large, but that sum here goes to 0. And so this is not basic analysis. This works. Of course, there are sequences such that the sum diverge, but the squares, sum of squares, goes to 0. And the simplest example is probably gamma k equal 1 over k plus 1. And use k plus 1 because k starts at 0. It would also be enough if the quotient of these two goes to 0 actually. This ensures that this sum diverges and this sum converges. Also gamma k equal 1 over square root of k plus 1 can also work, but in this case you still have that this quotient still goes to 0, even though this still diverges. So sum up here, but this diverges faster, so this still goes to 0. It would also work. So let's show that. So what can we expect now? So we have a meaningful choice, and we kind of know it has to work because at least under this choice, this goes to infinity, this goes to 0. The quotient has to go to 0. So what happens in this case? Let's analyze a little bit further. And so what we do now is we would like to estimate quantities like this by some non-expressions. And the simplest thing to express these sums or approximate these sums is by comparing to the integral. And how does this work? Okay, so here's n, and let's say you have the function f, which is defined on the interval of, let's say, some k minus 1 to n plus 1 into the real numbers. So here's again also we need an n plus 1 and the k minus 1, and it's decreasing so that it goes like this. So then the sum of the fk's from capital K to capital N, you can kind of picture it graphically like this. So that is the sum here. And then you see you have a lower bound on this sum by integrating the function f from k to n plus 1. From k to n plus 1. And you have an upper bound by shifting all these things to the left one step, and you have an upper bound by integrating from k minus 1 to n. So these are simple upper bounds if you have a decreasing thing. So what you get here now is this is smaller or equal to, because you have to take care a little bit of the 0, it's 1 plus integral from 0 to n over 1 over x plus 1 dx, and this is, so it shows that this goes like the logarithm. And also you have a lower bound for this guy here. This is the integral from 0 to n plus 1 over 1 over x plus 1 dx, which is log of n plus 2. So it really shows that this sum here behaves like the log. So it grows like the log. Okay, similarly we can do the same thing for 1 over square root of k plus 1 from 0 to n, upper bounded by 1 plus integral 1 over the square root of x plus 1 dx, 0 to n, and this is 2 times square root of n plus 1 minus 1 if you do the algebra to calculate that. And the lowest is again the same integral over here, and it's 2 times square root of n plus 2 minus 2. So this goes here like the square root. So the sum of the inverse square roots go like the square root. And finally we also need 1 over k plus 1 squared from 0 to n, same thing. We don't interested in the lower bound here, but the upper bound can be something like 2 minus 1 over n plus 1. So this is actually a convergent sum right here. You know, this converges, so it's here you have an upper bound here like 2 minus something. Okay, so let's put it together, and then that's where all the typo starts here in the handout. But anyway, okay. So let's consider step size here. If you now choose gamma k being 1 over k plus 1, so it's summable, square summable but not summable, and that is the the thing which we considered here. So it's square summable but not summable. So what we get then we get f best n minus f star smaller equal. And now what I do is I use here I use this upper bound, the upper bound on the squares up here and the lower bound on the sums down there. So and then you get, now to write it carefully, L square over 2. For this, I need this upper bound. It's 2 minus 1 over n plus 1 plus this constant. And down here, it's the lower bound log of n plus 2. Okay, and you see it actually goes to 0, but very slow. So this goes to 2 from below, and this goes to infinity, but like 1 over log. Sheesh, that's slow. But okay, it does go to 0. You know that before, but anyway. So, but it's kind of an O of log n, and this is painfully slow. If you take 1 over square root of k plus 1, things look better than the best function value is, and again, just for typos, L squared over 2, so upper bound. So if this is the case, then use this upper bound over here for the sum of the squares, which is 1 plus log of n plus 1 plus d squared, and divided by a lower bound for the square roots, which is 2 square root of n plus 2 minus 2. And again, this goes to 0. And it looks better, right? So this goes to infinity logarithmically, but this goes to infinity like the square root. So it's like log over square root, and this is kind of a little bit slower than 1 over square root. But it's log over square root. So one could say kind of this is like an O of log of n somehow, and it's an O of log n over square root of n. So basically, and this is faster than that. So that's also is 1 over log. That's faster than this, but it looks painfully slow. Okay. These both things are valid. It works, but why can't this typos? There's another way to view it. So what this is again, so it's not that bad. So we get an estimate on a computable quantity. Okay, the estimate cannot really be computed because you don't know the d squared. But you know at least the order in which this has to go to 0. So you have an upper estimate, at least the order, so constant times a term like this, unknown constant, but anyway, for a term you can really calculate. Sometimes you may even estimate this thing here, right? For example, if C has bounded diameter, and you start inside C, you know that this d squared is not larger than the diameter squared over 2, which is not that bad. Then you have really a computable estimate. You know this, you will be this good in this amount of time. And that's actually one goal for optimization, right? You want to know how much work you have to put in before you start. Or you would like to know how good you are at a certain point without knowing the answer. And this gives you a guarantee of that type, actually. Okay, another way to view it is choose a step side with the termination time in mind. So here it's like this works for all n. You iterate for n, you get this guaranteed upper bound. The further you iterate, the smaller the upper bound gets, and everything still holds for all n. You could also think about it in the way like, let's do n steps. How good can we, what can we guarantee in n steps? So fix capital N in advance. So actually it's n plus 1, I guess. Oh no, it's n. Did I do something wrong here? No, I think it's fine. No, it's fine. It's capital N. So if you fix n in advance, our upper bound looks like, let's check again. This upper bound looks like L squared over 2 gamma k squared plus d squared divided by the sum over the gamma k's. So that is what the upper bound involves. Oops. And k goes from 0 to n. Okay, and so what we want to do is we would like to make this thing as small as possible with n fixed. So we consider this as a function of all the gammas. So gamma is now the vector, gamma 0, gamma 1 to gamma n. And this is a function of gamma. Okay, we would like to minimize it. We would like to minimize the guaranteed upper bound which we have on what we would like. So minimize that over gamma. And so what we... so what we do, we take the gradient of r and set it to 0. So and what is it? It's actually not that hard to compute. So what we get? The derivative of this times that. So when you take partial derivatives, so the derivative with respect to gamma 0 of the numerator. So this is just gamma 0 squared plus gamma 1 squared plus gamma 2 squared. Taking the derivative gives just 2 times the gamma for which you take the derivative. Yeah. So the derivative of the upper thing here is just L squared times gamma as a vector. The 2 cancels out. And then you have to multiply. There's no square here. Multiply by the denominator, which gives you this. So you have to subtract this guy minus that. This guy is L over 2 times sum of the gamma squared plus d squared times the derivative of that. So the derivative of that it's even simpler because this is just gamma 0 plus gamma 1 plus gamma 2. If you take the derivative with respect to some gamma, you get 1. So this is just the ones vector. So this here is the vector of all ones. Okay, and then you divide by the square of the denominator, which is actually irrelevant for it. And you want to set this to 0. Okay, so the good thing is now here, so that these are the only vector valued quantities here. That's a scalar, that's a scalar, that's a scalar. So it's only like this. So what you get here is, if you maybe just shuffle it around, that gamma is equal to, and then it's a little bit complicated, it's L squared over 2 gamma k squared plus d squared like that, divided by L squared. This here's the sum of the gammas again, but here's the ones vector. And you see, even though the gamma also appears on the right hand side, you see that the gamma has to have all entries equal, because it's a multiple of the ones vector. So this shows you that gamma is actually h times the ones vector, just from here. You don't know the h. So, but once you know that, you can kind of bootstrap your ones up and plug it in here, and then you get an equality, an equation for h. So this h has to fulfill, h has to be the same as. So this is the vector of all h's. Has to be like this. It has to be 1 times this, and I plug in h for each of these summands over here, and I get, let's see, so I have to calculate it on the fly. It's n times h squared plus d squared divided by L squared times n times h. Yeah. Okay, that's that. And let's reformulate it a little bit. So if you multiply that through by L squared nh, you get L squared and h squared equal to L squared over 2 and h squared plus d squared. So there was something different here, but okay, let's see. I hope I don't make any typo here, otherwise I have to correct the video, which is painful. Okay, let's double check. This is L squared over 2 times n, because this is n times h squared. That's n times h. L squared is still here. Where does this L squared come from? From there. This was this L squared. Okay, gamma. Let's see, gamma here. I think that's true. Okay, so what is this? We move this to the left hand side and then have L squared n over 2 times h squared equals d squared, which then evaluates to h squared is equals to 2 d squared over L squared n. And since you only have positive step size, we can take the positive square root, which gives then square root of 2 times d over L times square root of n. And it's different from what I had before, but it's not too far off. Okay, so this gives you a precise thing what you should do to get the best upper estimate for the best function value among the first n iterates. Remember that what we did was we minimized we minimized this upper bound here, right? This is the distance of the best to the optimal. We minimized this upper bound for n fixed, and so this gets as small as possible if you take this h here. So h should be of the size of 1 over square root of n. Okay, then you may know the subgradient, that's nice, but you don't know this d actually, and this is bad, because if you change this d, this is not optimal anymore. A constant step size, depending on the d, can be basically still any positive number. So it's really, it's again not too helpful. What you can do is to plug that in here and calculate the estimate, and we're going to see that this kind of behaves like O of 1 over O of so this, I don't do the calculation here, but so this f best n minus f star is then estimated by something like O of 1 over square root of n and nothing else, which is somehow the best thing which we've got up to now. So we can do it like this, choosing 1 over k plus 1, then we can only guarantee a decay of 1 over log, which seems awfully slow. If you choose 1 over k plus 1, square root of k plus 1, you get log n over square root of n, which is better but still painfully slow. But at least if you keep iterating, these hold always true. If you keep adding more iterations, this always holds true. If you fix the number of iterations in advance and choose h like this, you will get 1 over square root of n without the log factor, so it's actually a little bit better, but it only works up to the nth iterate. After that, nothing can be guaranteed anymore. So this is the constant, so it doesn't go to 0, and actually the upper estimate here has to explode in this case. So the conclusion is subgradient method works. It reduces the distance to the optimum, to any optimum, as long as the step sizes are small, but you don't know how small. Choosing step sizes is a pain, so you can only guarantee very slow convergence here. It's really, really slow. So these things work, but we're going to see in a minute that you could, of course, also use c times, constant times 1 over k plus squared. This always fulfills and also has to go to 0, and the same estimate here also, the same order still applies, but you get a different upper bound, and you can try to optimize over the c here, and you'll see it still depends on unknown quantities. And in practice, it does affect convergence a lot. If you take 1 over k plus 1 or 10 over k plus 1 over 0.1 over k plus 1, they all look very, very different. And you don't know what to take before you start the calculation. So it's really a pain. And this here is even more painful because you can then iterate up to n, and then at that point you don't know, so you shouldn't stop. You're not satisfied. So what should you do? How should you proceed any further? And probably what is behind this is, at least from my understanding, is that in the non-smooth case, the magnitude of the gradient doesn't tell you anything about how far you're away from the solution. So just consider that you have a function like this, where the minimum is at a kink, but you can be very, very close to the minimum right here and still have a huge gradient pointing to the right direction, but you don't know how far to go. If you have a smooth function, and here's your minimum, and you are here, then you know that if a sequence converges to the minimum, then the gradient has to go to 0. Here it's not the case like that. Okay, so I have a numerical experiment to show you, and the numerical experiment is very, very simple. It's just f of x is ax minus b 1 norm. Actually, I thought I included a plot already. No. It's called least absolute deviations. Absolute deviations, LAD. Also, yeah. Also minimum absolute deviation, which would be abbreviated MAD, which is also nice. And it makes sense. It makes sense, for example, if you want to do regression, but don't have Gaussian noise in the B, but different noise. And if I remember correctly, it's Laplace distributed noise in B, then this is the right thing to do. Okay, and this is not smooth, but it is like it's like g of ax, and the g of x is just x it's of y, let's say it's just y minus b, 1 now. So it's a concatenation of this convex function non-smooth and the linear operator, and so by and then also this is continuous everywhere. It's continuous everywhere, so that means subgradient rules apply. So because g is continuous everywhere, subgradient rules apply, and the subgradient is then just be a times the subgradient of g at ax. So what's the subgradient of g? Subgradient of g of x is actually the subgradient of, I just write it like this, at y, and we did take the subgradient of the absolute value once. So this was if you just have the absolute value, say h of x is the absolute value, then we calculated that the subgradient is actually minus 1, 1, or the full interval, x negative, x positive, x equals 0. Oops, here we go. And this is what is commonly known as the multi-valued sine function. It's the multi-valued sine. Okay, so, and we can just plug it in here, and this gives 8 times the multi-valued sine of ax minus b. The translation, there's a rule for that, translation just translates. Okay, so we get one subgradient for free. We just calculate ax minus b and take the usual sign, a times the usual sine of ax minus b, and the sign applied component-wise. And also this is applied component-wise. So that's one subgradient which you can always take. So, and we don't take, the c is the full RD. Actually, we don't do any projections. We don't have to. Then it's just the subgradient method. Okay, let's do it. Yeah, I did it. There it is again, and where is it? That's the plot. So what I plotted here is, because I don't know the minimal value, actually, I was too lazy to figure it out, I just computed the value of fk best, so after k iteration. This is k here, and that's the value after k iteration. Oh, so sorry. This is k here, and this is the value, the best value you get after k iterations. And if I don't plot the best value, only the value, it really wiggles up and down a lot. So what you see here, so the blue one is the 1 over k plus 1 step size. So the blue one here is 1 over k plus 1, and it goes down fairly quickly in the beginning, and then it levels out. It has to level out because it has to converge. 1 over square root of k plus 1 goes down slower, and in the end it's still worse. But these here, the fixed step size, which is now fixed at the 1000 here in the end, it goes down in the beginning pretty fast, but then it really struggles to improve any further. And have a factor of 0.1 in the front of here, actually, always. It's 0.1 over k plus 1, 0.1 over square root of k plus 1, or 0.1 over square root of n plus 1, the final iteration. And so, this is how the picture looks in this. If I change the step sizes, just the constant in front of it, to 1 for all of them. Let's do it, or let's do not 1, because let's do it over 1.5. So just a second. Oh, and there actually was, it was 0.5. So I think there was something slightly. Okay, if we take 0.5 for all of them, the picture changes. So now the constant step size keeps being better as the 1 over square root 0.5 over square root of k plus 1, and this is still the best. But I think I can turn the figure around by, let's know, taking 2 times And it all has to work, right? They all have to work. There's one more up here. But no one guarantees how good they are. So now a larger constant in front of it, and kind of, oh yeah, the picture really. So this is still the best. That's very bad. And the red line is just, you can't see it anymore. It's just too up high. Okay, and so you can play around with this as much as you like. So if you take 0.01, let's see what comes out. So it's really a pain. Of course, you can always observe the descent of your method, how the f best gets smaller and smaller, but you have no idea how far you're away from the minimum or how far the minimum value is away, because all the estimates we have, none of them is explicit enough to guarantee anything. So that's now with very small step sizes, 0.01 in front. So let's have a look here. Oops, like this. Yeah, so now it appears that the square root is better. And so it really, but also the other step size, the constant one, kind of performs, I guess, almost as good in the end. Okay, but it's really hard to say who is the winner here. It's really kind of impossible. So even for this very simple least absolute deviations, it's really hard to figure out a good step size, even though basically everything is known in advance. We could figure out the L, the Lipschitz constant. We could at least estimate it. It's almost already here, so we can. But it's difficult. It's still it's not that simple. And also the distance to the minimum is really kind of impossible to estimate. Yeah. Okay, so that's it for today. Next lecture we're going to talk a little bit more about algorithms in the convex case, and have some more analysis of algorithms. So what we do here is we analyze algorithms which are very simple. So it's a one-liner to implement, more or less. So maybe I could have written it down. So what you just do here for the algorithm is just xk plus 1 is xk minus gamma k times a times the sine of a xk minus b. So that's just this. Just type that in and choose gamma k, and you have an algorithm, and it does converge, but painfully slow. Okay, and this it will be true that the algorithms that you're going to derive are also still very simple. There's no much tuning around. We always try to derive algorithms which are so simple